Okay, so this is section 4.9, and just to give you a little bit of background before we really delve into this, one of the things I really like about this section is I think it kind of connects the centuries for us. So this is called Newton's method. It was, this was an idea that was first developed by Isaac Newton, and it's been built on, quite a bit over time. But what Newton wanted to do was create a way for finding solutions to equations that were hard to solve, and in the 17th century didn't have access to a computer to just do it for him. you know when you wanted to compute stuff, you had to do everything by hand, and it was really painful. So these methods were kind of necessary to solve problems and to actually do math in a practical way. um, Now that we have computers, these methods aren't any less useful, they're just more hidden. um, when you ask your calculator to compute something like the square root of 2, your calculator doesn't know how to do a square root. The circuitry in microchips can like add and multiply just fine, but they can't do things like square roots. You kind of have to teach your calculator what to do. So if I asked you to take a square root by hand, you'd be like, what do you mean, right? So this gives us a way to do things like finding square roots and solving basically anything that we want to solve that doesn't have a nice integer solution. Um, so we have these complicated equations like, okay, solve a fifth degree polynomial, or solve tangent x minus x equals 0. Okay, and these aren't things that you can just write down and get a nice number for. The answers are irrational numbers, and we don't have a nice way to write them, and we don't have a nice way to solve these equations. So what we're going to do is we're going to find a way to get a numerical approximation. Now, we talked about numerical approximations earlier, right, when we did linear approximations. The problem with that section was we found a linear approximation that maybe was accurate to 2 decimal places, but that was it. And if I'm, say, designing a microchip for my calculator and I want to display 10 decimals of accuracy on the screen, then 2 decimals of accuracy isn't going to cut it. So the idea of Newton's method is that you can continue to do more work to get as much accuracy as you like. So if I need 5 decimals of accuracy, I do so much work. If I need 100 decimals of accuracy, I just do more work, and I can get all of those, right? There's no limit to how accurate our answer can be. We just have to keep doing work to get there. All right, so here's a visual of the idea for what we're doing with Newton's method. So let's suppose I have some function, right? So this curve is, y equals f of x. And what we want to do is solve f of x equals 0. Okay, and we'll look at how this relates to doing something like finding a square root later. But I'm trying to figure out where this function has a 0, right? So, that would be this point here. So what we do is we first start with an initial guess. So this is like, starting point A. I have some initial guess, and if I plug that into the function, that's not right. That doesn't give me 0. Okay. But what I do is I approximate my function with a tangent line, just like we did with the linear approximation section. And instead of trying to figure out where my function hit 0, I can figure out where the tangent line hits 0. Okay. So this line here is my tangent line, and where it's hit 0 becomes my next guess. Okay, so then when I plug it into the function, I see, is that close to 0 or not? And if I want to keep going, I find a tangent line at that point, figure out where that tangent line hits 0. And I can repeat this process as many times as I like. And that's the idea behind Newton's method. Okay, so it's like finding out, instead of where the function hits 0, finding out where the tangent line hits 0. Now, the way I've written this is kind of a multi-step process, right? I start with a guess, then, I plug in to be able to find the equation of the tangent line, and then I figure out where the tangent line hits 0, and that's my next guess. So that was multi-step. What we want to do is see if we can boil this down to just being like a one-step process. If I have a guess, can I compute the next guess in one formula? Okay, so that's what we're going to do. Let's see if we can figure that out. So first of all, let's get a reminder of, if I have a generic function f of x at x equals x0, can I write the equation of the tangent line? So remember the general formula we had, right? Y minus y0 equals m x minus x0. That was our point slope equation for lines. If I want it to be a tangent line to y equals f of x, then the slope is going to be f prime, where I plug in my x0. And the y value is just f of x0. Okay, so this is going to look like y minus f of x0 equals f prime of x0 times x minus x0. And if I solve for y so that I get a nice y equals equation, I just add f of x0 to both sides. Okay, so this is the equation of my tangent line, and I can label this as something like L of x. Okay. All right, so this is the tangent line to f of x at x0. Okay, now if I want to figure out where does that tangent line equal 0, right? That was sort of our next step, right? First we find the equation of the tangent line, then we figure out where the tangent line hits 0. Okay, so what I'm going to have is f of x0 plus f prime of x0 times x minus x0 equals 0. And my variable here is x. Okay, so I want to solve for that. So I want to peel everything else away. So I'm going to subtract f of x0 from both sides. Okay, then I'm going to divide both sides by f prime of x0. And I can only do this if the derivative is not 0. So if the derivative is 0, which means I have a horizontal tangent line, then Newton's method just fails. It breaks down and I don't get to proceed. So we'll talk about that later on. Okay, so x minus x0 is negative f of x0 over f prime of x0. And now to solve for x, I just add x0 to both sides. Oops. So instead of a plus, because I have a negative here, I'll just write this as minus f of x0 over f prime of x0. Okay, and so this is my formula, or this is going to become my formula for Newton's method, because this gives me the x value where the tangent line hits 0. So if I plug in a guess x0, then that point where the tangent line hits 0 is my next guess x1. Okay. So in general, what we do is we say, all right, if I want to find out where a function hits 0, using x0 as an initial guess, then a formula for my next guess, xn, is take the previous guess minus f of the previous guess. We're missing a parenthesis there. Over f prime of that previous guess. Okay, so let's take a look at this. Okay, so this was one of those terrible examples that we had in the beginning where we said that you can't solve this by hand, right? What I want to do is I want to figure out where this function equals 0. So I'm solving this 5th degree polynomial equals 0, and I'm going to use an initial guess of 1. Okay, so first let's set up what Newton's method looks like. The formula xn is xn minus 1 minus f of xn minus 1 over f prime of xn minus 1. Okay, well here's my function. Let's write down what the derivative looks like. The derivative is 5x to the 4th minus 6x. Oops. Okay, 5x to the fourth, when I bring the 3 down, it'll be minus 6x squared. Bring the 2 down, it'll be minus 14x, and then minus 4. Okay, so my formula then for xn, for the next guess, is take the previous guess minus f of the previous guess. Yeah, I guess we'll just write it down. It's long and messy, but we'll write it down once. Okay, so I have xn minus 1 to the fifth minus 6 xn minus 1 to the fourth plus 2 xn minus 1 cubed minus 7 xn minus 1 squared minus 4 xn minus 1 plus 10. Okay, over the f prime. Oh, did I skip a term? I think I skipped that one in my f prime. Let's throw that one in. When I bring the 4 down, I don't know how that got missed. All right, when I bring the 4 down, it'll be minus 24x cubed. Oh, and then this is plus. Yeah, I don't know what's going on with me today. I'm just kind of combining these two together in some strange way. Okay. All right, so let's look at what this looks like. When x0 is equal to 1, then x1 is, I'm going to plug 1 in to this whole thing. So I get 1 minus 1 to the fifth minus 6 times 1 to the fourth plus 2 times 1 cubed minus 7 times 1 cubed, 7 times 1 squared minus 4 times 1 plus 10 over 5 times 1 to the fourth plus 6 times 1 squared minus 14 times 1 minus 4 minus 24 times 1 cubed. Okay, so I'm going to get out my calculator and I want to do two things here. I want to show you, plugging this in and the number I get, but then I also want to show you like a quick way to compute values here. Okay, so 1 minus, and then I'll put this thing in the numerator. 1 minus 6 plus 2 minus 7 minus 4 plus 10 divided by 5 plus 6 minus 14 minus 4 minus 24. Okay. It's kind of a mess. All right, and we get 0.8709. I want to make sure I write all of these down.
I think it's supposed to be minus 6 in the denominator.
It is supposed to be a minus 6. I feel like that one problem mixed up these two terms right at the beginning, and then everything got messed up from there. So that's a minus. That's a minus. That's a minus. Wait, where's the plus? Oh, no, sorry. In the denominator, what I did was, because I skipped this term, I put it at the end.
Okay, yeah, you're right. Sorry about that.
Okay, so I think that one is a plus. Okay, but yeah, that's what I get for making things messy. Okay. All right, let me show you a way to do this on your calculator without nearly the amount of hassle. So what I'm going to do is, I'm not actually going to graph this, but I'm going to hit the y equals, and I'm going to plug my function in as y1. So we have x to the fifth minus 6x the fourth plus 2x cubed minus 7x squared minus 4x plus 10. Oops, that's not that one. And then I'm going to just put the derivative in as the next function input, right? So 5x to the fourth, and I'm not going to do this crazy out of order business. So minus 24x to the third plus 6x squared minus 14x minus 4. Okay, then if I started with an initial guess of 1, then my next guess is my previous guess minus f of my previous guess. So if I hit variables, y variables, function y1, and I want to input this number 1. So I'm just going to hit answer, and I'll show you why in a second. Divided by this 1 plugged into the derivative. Well, the derivative is my y variable function y2. I put in my previous answer. Okay, so now I'm going to take 1 minus 1 plugged into the function divided by 1 plugged into the derivative, and I get that 0.87069, right, that we just computed. But if I hit enter again, it's going to do the same thing, except it's going to use this input as my next guess. So that tells me that x2 is 0.8537 and change. Okay. And then if I just hit enter again, it goes again, and I see, well, that 0.853 stayed the same, and it's just digits afterwards that changed. So I can write my x3 now, 0.853. I'll write the remaining digits, 4, 6, 7, 4, 3, 5, 1. Okay. And now when I go to the next one, I've got another 3 digits that are the same. So x4 is 0.85346734646. And then when I go to my next one, all of the digits are the same, which means every time I hit this, they're always going to be the same. So that means that after 4 rounds, I actually have 10 digits of decimal digits of accuracy. Okay, now you can ask yourself, how did someone like Newton get away with this? That was a lot of terrible computation. Well, yeah, if you have a messy function, there's a lot of work to do. But like, if I wanted to solve this 5th degree polynomial, and you just asked me to solve it by hand, like I would just sit here and scratch my head all day. I wouldn't have a way to proceed. Here, what we do is we say, well, doing adding, subtracting, multiplying, and dividing, which is all stuff that you can reasonably do, it's just time consuming, we can get to an answer. Okay, and more importantly, your calculator can solve it. And this is basically how your calculator does all of its computing stuff. Okay, it's just really quick, so you don't notice it. All right, let's look at another example. Find the square root of 2. Okay, so same idea. What we're going to do is we're going to say our initial guess is going to be 2. I know the square root of 2 is not 2, but, got to start somewhere, right? And, what we're going to do for our function, we kind of have to create one. So I have a graph here, and you'll see where this comes from in a second. to find the square root of 2, what I'm going to do is I'm going to say, let's let x equal the square root of 2. Oops. So then x squared would be 2. So x squared minus 2 is 0, and now I have a function equal to 0. Right? So we're going to let f of x be x squared minus 2, and that's why I give you the graph here of x squared minus 2. So I can turn this square root problem into a function equal to 0. And we need this setup in order to do Newton's method. Newton's method is always solving a function equal to 0. Okay, so we let f of x equal x squared minus 2. So f prime of x is 2x. And then the formula for Newton's method is going to be xn minus 1 minus, take that previous guess squared minus 2 over 2 times that previous guess. Okay. So if my x0 is equal to 2, my x1 is going to be 2 minus 2 squared minus 2 over 2 times 2. So 2 squared is 4, minus 2 is 2. So I have 2 minus a half, or 1.5. Okay. And then my next guess is going to be 1.5 minus 1.5 squared minus 2 over 2 times 1.5. Which comes out to 1.416 repeating forever. Okay, again, I'm gonna have my calculator help me out here, just because I don't want to do a lot of basic arithmetic. Okay, so for this one, my function f is x squared minus 2, and my function f prime is 2x. Our initial guess was 2, and so what I want to do is I want to take my previous guess minus that previous guess plugged into y1 divided by that previous guess plugged into y2. So variables, y variables, function y2. I plug in my previous guess. Okay, so there I can see the 1.5 that I computed. I can see the 1.416 repeating computed. And then let me write this one down really quick. x3 is 1.414215686. Okay. Then x4 is 1.414213562. And the next step, the x5, is the same as x4, so no change means we're done. So this is accurate to, maybe only giving me 9 places here. I could have sworn we had 10 up above. Yeah, that's weird. Oh, because the 1 in front. Okay. Okay. So it only took us 4 iterations to get 9 decimals of accuracy. So we'll give you some way to put that into context later. But for now, you can just think that Newton's method is actually pretty fast. Okay. Oops. All right. So let's look at some things that are wrong with Newton's method. One of the things that can go wrong is, let's suppose that I'm looking for this place here where the function hits 0. My guess is over here, the tangent line is going to hit over here and get me really close to this root. And of course, the next tangent line is going to almost hit that root. Right? Okay, so one of the problems can be Newton's method may not always find the root that is closest to your initial guess. Okay, so that's something to be aware of. Okay, right? It's quick, but it can be a little bit crazy. The other problem, and we talked about this a little bit, in the formula for Newton's method, I'm dividing by the place where I plug in to the derivative. So if I plug into the derivative and get 0, which means I have a horizontal tangent line, the formula breaks down. And if you were to look at a graph, what will happen is if I have a horizontal tangent line, that never hits the x-axis, and that's why it breaks down, right? If I were to, have a guess here, and I get this horizontal tangent line, the tangent line never hits the axis. It doesn't have a 0, so I don't have a next guess. Okay, so if a guess has a horizontal tangent line, then the whole process just fails. I get something undefined. If I hit on the graph not exactly on a horizontal tangent line, but close to it, then that can also be problematic. All right, so I'm going to just say it may get messy, and here's the ways it can get messy. Let's suppose I don't hit the horizontal tangent line exactly, but I hit close. All right, what may happen is that I might have my next guess being very, very far away, okay? And it might take a lot of iterations for it to come back. Or we could have an example like this, where I don't exactly have a horizontal tangent, but if I plug in, let's say, 1 for an initial guess, my tangent line hits 0 here. I plug in 0 for my next guess. The tangent line hits back here at 1, and it just bounces back and forth between 1 and 0. Okay, and I'll show you that with the formula, right? So my f of x in this example is x cubed minus 2x plus 2. F prime of x is 3x squared minus 2. So our formula for Newton's method so if I put in the function, so we get our input cubed minus 2 times the input plus 2 over 3 times the input squared minus 2. And let's suppose that x0 is 1. Okay. Then x1 is going to be 1 minus 1 cubed minus 2 times 1 plus 2 over 3 times 1 squared minus 2. So I have 1 minus 2 plus 2, which is 1. 3 minus 2 is 1. 1 minus 1 is 0. Okay, so x1 is 0. That's no problem. So then x2 is going to be 0 minus 0 cubed minus 2 times 0 plus 2 over 3 times 0 squared minus 2. So I get 2 on top, negative 2 on bottom, minus a negative is plus, 2 over 2 is 1, so I get 1. But I already know if I plug in 1, I'm going to get 0, right? So this is just going to go back and forth. Okay, so it never hits a root. And what happens here is, because I have a dip in the graph, but it doesn't actually hit 0, right? It's, over here it's looking for a root to the left, over here it's looking for a root to the right, but the root isn't actually there. Okay, so Newton's method can get faked out sometimes. Okay, so these are some of the issues with Newton's method. but otherwise it's pretty robust. So let me just give you some comparison, right? So Newton's method, we had some pros and cons here. One of the pros is that it works really fast, and I know that you don't really have a good basis for comparison, so I'm going to give you something else that could solve this problem, okay, that we maybe alluded to but didn't go into detail. Okay. But some of the downsides of Newton's method is it's a little bit sensitive to your initial guess, and it can be a little bit sensitive to the function. Okay, so just to give you a comparison, I want to show you something else that can do the same thing. So this is called the bisection method, right, rather than Newton's method for finding roots. So if you remember back to chapter 2, we talked about the intermediate value theorem, and it said, all right, if you have a continuous function and one value is negative and another value is positive, then it has to hit 0 somewhere in between. Okay, so we can turn that into a method for finding zeros, right? So to give you an example, let's look at this same problem, right? Finding the square root of 2, right? Remember, to find the square root of 2, we're essentially solving x squared minus 2 equals 0. Okay. So this is finding the square root of 2. Now, this gets really messy with a bunch of computations, so I kind of wrote this all out ahead of time, right? So we're going to start with the interval 1, 2. One of the things with the bisection method is instead of initial guess, you need 2 initial guesses, right? And you need to make sure that your root is somewhere in between. So there is some, guesswork here too. All right, so here's my function, and I'm going to say, all right, if I plug in, oh, I plugged in 0. I meant to plug in 1. I want to start by plugging in 1. If I plug in 1, f of 1 is negative 1. F of 2 is 2. So what we do is we go halfway in between them. Halfway in between 1 and 2 is 1.5. Okay, so then we check 1.5. I plug that into the function. I compute it's positive, right? So when we started, this 1 gave me a negative, and this 2 gave me a positive. So I know that there's a 0 in between. Halfway in between, I get a positive. So I'm going to replace my bigger positive with this smaller one. So once again, the 1 gives me a negative, the 1.5 gives me a positive, so there has to be a root somewhere in between by the intermediate value theorem. So again, I go halfway in between those two. I get 1.25. So then I check that one. I plug it in the function. I get a negative. So what I'm going to do is I'm going to replace my old negative value with this slightly bigger one. And I know the root is somewhere in between 1.25 and 1.5. So again, I go halfway in between, check it, I get a new negative, so it replaces the old negative one. I go halfway in between, I check it, I get a positive, so it replaces the old positive one. I go halfway in between, I check it, I get a negative, so it replaces the negative one. Since I know that the root is in between 1.40625 and 1.4375, I know the root has to look like 1.4 something. So far I have 1 decimal of accuracy, right? So after 1, 2, 3, 4, 5 steps, I have 1 decimal of accuracy, okay? And we can keep going. And because I'm cutting my interval in half at every step, after 3 steps, that's 1/8, which is close to a tenth. So it's a little bit more than 3 steps to get another decimal of accuracy, okay? So that just gives you an idea for how fast this method works. Newton's method, for comparison, after 4 steps, I had 9 decimals of accuracy. Okay, and here, after 5 steps, I have 1. Okay, so we can see that Newton's method is quite a bit faster. So if you're, you know, a Renaissance era mathematician and you're computing by hand, you would say, yes, this would save me like a whole day of work to have, only 4 steps to do, instead of to get the same accuracy, like 30 steps, okay? On the flip side, when we go to the computing age, I don't feel like this becomes less important. I feel like it becomes more important, okay? If you've ever used a computing device of any kind, be it a computer, a phone, or, an elevator, anything that's doing some sort of computation, and it's slow, it's laggy, you're like, oh my God, I wish this would just, would just work, okay? When you can make software faster, everything works better, okay? And this is on the software side of things, right? If we can implement a way to solve things, right? If you need to compute stuff and it takes a long time, then you need a lot more processing power or a lot more time to do the same task, right? So that's the difference between things happening like instantly when you push a button and things, seeing that slow thinking circle of, pain and dismay, right? So like, um, this I feel like for some people this should be like the most relevant section of calculus because this is sort of fundamental to how all of our computing works. Okay, so if you're going into computer science at all, right, this is probably a really, hopefully this is an interesting topic. All right. You won't see any questions on the bisection method, either on the homework or on an exam or anything. This was just to give you like a little bit of frame of reference. And the reality is that the bisection method, it doesn't have these weaknesses where it gets stuck and doesn't find a root or jumps way off. And so what computers typically do is use a combination of methods, right? You can use something like a bisection method to get you somewhere near a root that you know exists, and once you're somewhat close, you switch over to Newton's method and you can get all of your decimals of accuracy really quickly, right? So you can use a bisection method to avoid the problems of Newton's method and have some sort of crazy combination of methods, okay? And that's more like what modern computing looks like. It's not one or the other. It's, a more complicated combining of different methods. And it's not just these two, but this is just kind of a nice introduction. All right, any questions on this stuff? All right, so that's Newton's method. Now let's flip over and take a look at section 410. All right, so 410 is on antiderivatives. And if 4.9 seemed like there wasn't a lot of computing by hand, well, then 410 will take care of that. Okay, so this is going to be, I feel like, back in line with the things that seem familiar, right? Taking derivatives. In this case, what we want to do is do the process backwards, right? So we're going to reverse the process of differentiation, and we're going to start by getting some of our terms straight. So the definition of an antiderivative, a function capital F is an antiderivative of little f if the derivative of capital F is little f, right, for the whole domain. So for example, if capital F is x squared, then capital F prime is 2x, which is what little f is. So capital F is an antiderivative of little f. Okay, suppose I look at g of x as x squared plus 3. Then when I take the derivative of capital G, I get 2x, and that's also equal to little f. So capital G is also an antiderivative of little f. Okay, so the first thing that we notice in our first example here is that antiderivatives are not unique. But we have some machinery to help us deal with this, to figure out what's going on. And if we go back to section 4.4, that was the section on the mean value theorem, and corollary 2 to the mean value theorem said that if I have these two differentiable functions and their derivatives match, then the functions are the same up to a constant, right? F of x is g of x plus some constant. Okay, and you can see that back here, right? I had x squared, and I had basically the same function, but just with a constant added. Okay. So although antiderivatives are not exactly unique, they are unique up to a constant. So when we solve for an antiderivative, right, in math, when we solve stuff, we want to find all the solutions. So what we want to do is we want to give all of the solutions. And we can do that by giving the family of all the antiderivatives. Okay, so if I have little f of x is 2x, then the family of all antiderivatives is x squared plus c. Okay, where every different number for c gives me a new function, and that family of functions is all of the antiderivatives of 2x. All right, so find the antiderivatives of f of x is 3x squared. So I need to come up with something such that when I differentiate it, I get 3x squared. Right? So what I could do is I could say, oh, okay, that'll happen if I start with x cubed. And if I put my plus c on there, then I get the whole family of functions. So this is all of the antiderivatives instead of just one of them. Okay. Find the antiderivatives of cosine x. Okay. Well, got to think about what can I take the derivative of to get cosine. I could start with sine x, and the derivative is cosine. So then we're good to go. Okay, so when I put that plus c on, I get that family of all antiderivatives. All right, now this is a little bit cumbersome when we say find the antiderivative. That's a lot of words. We want to change this into some symbols so that I can just write this as, you know, a math equation instead of having to write a bunch of words. And so I'm going to introduce some notations, but also a new word for it, right? So antiderivative seems like a very intuitive idea, like I'm just undoing the derivative, but we're going to call it something else. And it's not really clear why we do that, and it will become clear in section 5.4. Okay, so for just a few sections here, right, for the end of chapter 10 and the beginning of, or sorry, the end of chapter 4, right, 4.10, and the beginning of chapter 5, we have to deal with this word integral, and then after that we'll be like, oh, that's why it's called an integral. Okay. All right, so if f is any antiderivative of little f, we say capital F of x plus c is the most general antiderivative, right? Because this is the family of all of the antiderivatives. And so if I want to take the antiderivative of little f, this is what I write. This is a two-part symbol, okay? So this is like an elongated s, and that's my integral symbol. Okay, and that means take the antiderivative. Okay, so then this is the integrand. Okay, and then I can see this dx on here. That differential is part of the integral symbol. So we have this weird two-part symbol. Okay. So the differential dx is part of the integral symbol. And it also tells me what the variable is. Okay. All right, so if I just write something like integral 2x, This doesn't make sense. Okay, but if I write the integral of 2x dx, then that's cool, I can find that. Integral of 2x dx means take the antiderivative of 2x where the variable is x. And I can say, well, I can think of what can I take the derivative of to get 2x? That would be x squared. And then I put the plus c on there. Okay. Now, if I think back to the Leibniz notation for derivatives, right? So dy dx is the derivative of y with respect to x. Okay. And we know that with differentials, we could split up the dy and the dx as separate pieces. Okay. But if I think of when I'm differentiating, I've got this dx in the denominator. When I'm doing the process backwards, I have the dx in the numerator, right? Or not in the denominator. Okay, that's not an accident. But again, this is something that we're going to explore in more detail in Chapter 5. The reason that we write the notation this way is because there's going to be this nice connection between writing an integral this way and taking a derivative. Okay, but for right now, we're just going to say this indefinite integral just is an antiderivative. Okay, and I think things will make more sense later when we do that. All right, so let's get to some integration rules. First, let's look at a power rule, right? So if I take a few derivatives, right, if I say take the derivative of x to the 10th, I get 10x to the 9th. Well, let's suppose I wanted to end up with just x to the 9th. Then if I take the derivative of 1/10 times x to the 10th, then when I differentiate, the 10 will come down and cancel the 1/10, and I'll just be left with x to the 9th. So if I want to undo this derivative, if I started with x to the 9th and I anti-differentiate or take an integral, I'll start with 1/10 x to the 10th. And so what I can do is, in general, I can say, well, if I started with x to the n, when I differentiate, the n comes down and I lower the power by 1. So if I wanted to have just an x here and not a coefficient out front, I'm going to start with 1 over n times x to the n. And then the n will come down and cancel the 1 over n, and I just get x to the n minus 1. And then I say, well, let's suppose that if I'm focused on the end result as my starting point, because I want to go backwards, I want my power to be 1 higher. I'm going to start with a power that's 1 higher. So I'm going to take the derivative of 1 over n plus 1 times x to the n plus 1. When I take a derivative, the n plus 1 comes down, cancels the 1 over n plus 1. So I just get x to a power, but I have to lower the power by 1. Okay, and so that's where I get this power rule for integrals. If I anti-differentiate, or if I take the integral of x to the n, I get x to the n plus 1 over n plus 1, right? Raise the power by 1 and divide by the new power. Okay, and then of course the plus c. But this does not work when n is negative 1, because I can look at this and say, well, I would get a divide by 0. But there's nothing I can take a derivative of and well, here, let's look at this another way. If I wanted to end up with, after taking a derivative, x to the negative 1, take the derivative of something and end up with x to the negative 1. Remember, x to the negative 1 is 1 over x. And I can say, well, I know something whose derivative I can find that will give me a 1 over x, right? That's natural log of x. Okay, so this power rule business for integrals works for any power except the -1 power, but we'll cover that separately. That's going to figure that with a log. Okay, but never mind that for now. Let's just look at this power rule. Here's an example. Find the integral of x cubed minus 5x squared plus 3x minus 7. Okay, so I'm going to look at this the same way we did with derivatives, right? I'm going to treat the added and subtracted pieces as their own separate pieces, and constant multiples just hang out. So I'm going to do the power rule on x cubed. So I add 1 to the power and divide by the new power. For the x squared, I add 1 to the power and divide by the new power. For the x, I add 1 to the power. Oops, should be a 2. Divide by the new power. Okay, and there's two ways to deal with the 7. One way is to say, if I started with 7x, then when I differentiate, I would get 7. Or I could think of 7 as 7x to the 0, and then use my power rule, right? When I do the power rule, I take x to the 0, add 1 to the power, so I get x to the power of 1, divide by the new power. Okay, don't forget the plus c. So we have 1/4 x to the 4th minus 5/3 x cubed plus 3/2 x squared minus 7x plus c. Okay, now let's go back to this log business. First, I want to take some derivatives. Let's look at the derivative of natural log of x. That's 1 over x. Okay, let's look at the derivative of natural log of the opposite of x. Using the chain rule, I have 1 over the inside stuff times the derivative of the inside stuff, which is 1 over x. Now, if I've been paying attention, then I feel like I have a real big problem. We said at the beginning of this that antiderivatives are unique up to a constant. That if I take two functions and their derivatives match, then they're the same up to a constant. ln of x, ln of negative x don't look the same to me. Okay, so what's the deal? What happens here is ln of x has the domain x is greater than 0. ln of the opposite of x, I can't plug in a negative into a log. So if I have a negative on the x, then the x itself has to also be negative. So I would get a double negative, and I would be taking log of something positive. So this has domains negative values. So these two functions don't have any overlapping domain. So even though they have the same derivative, that's okay. They can be different functions because the domains don't overlap. All right. What this means for us is when we go backwards, if I want to find an integral, 1 over x has domain anything except 0. I could plug positives or negatives into 1 over x. So what I want to do is I want to have an antiderivative that has a domain just as big, if that's possible. Okay, so what that means is that for x's that are positive, I want ln of x. For x's that are negative, I want ln of negative x. So I would really like it if I could write x if x is positive, the opposite of x if x is negative. Okay, but this piecewise function is exactly the absolute value of x. So when I take the integral of 1 over x dx, what we're going to do is we're going to write ln of the absolute value of x. And the reason for that is so over here my domain is everything except 0. And over here on the right, my domain is just as big. It's all x's except 0. So I've preserved as much of my domain as possible. If I leave off the absolute values, I've ended up cutting my domain in half unnecessarily. Okay, let's look at another derivative rule. This next one is going to be nice. The derivative of e to the x is e to the x. So the integral of e to the x dx is e to the x plus c. That was nice and easy. No funny business with that one. All right, so based on taking derivatives, we can find a bunch of integral formulas. So I've just sort of summarized these. I don't want to go through them one by one, but we've already gone through the first few of them. Okay, I sort of skipped over this first one. We did it in the middle of a problem, but since the derivative of a constant is 0, well, I guess this isn't the same. The derivative of a constant is 0, and the derivative of just x by itself is 1. Okay, so if I integrate a constant on its own, I get a constant times x to the 0, which is a constant times x. You don't necessarily need to connect these two, but this is basically it. If I'm integrating a constant on its own, I get that constant times x. Okay. This next one we talked about, this is called the power rule. Okay, if I integrate x to a power, I get, add 1 to the power and divide by the new power, as long as it's not 1 over x. We have a separate rule for that. If I integrate 1 over x, I get ln of absolute x, and we just talked about that. We just talked about the integral of e to the x is e to the x. Okay. And then what we have is a list of all of our trig functions. Okay. Now, for the trig functions, what we're going to do is we're going to start with what I'll call the low-hanging fruit. The derivative of sine x is cosine. So when I integrate cosine, I get sine. Makes perfect sense. Okay. The derivative of cosine is negative sine. So going backwards, if I didn't start with the negative, then I would have to have the negative at the end. So it's backwards. The integral of cosine gives me a positive sine. The integral of sine gives me a negative cosine. Okay, so be careful with integrals. The negatives are backwards here. Okay, when I look at the derivative of tangent, I get secant squared. That means that I can find the integral of secant squared x, but not necessarily the integral of tangent x. I don't know anything off the top of my head whose derivative is tangent x, so I don't have an integral formula for tangent x. But I do for secant squared x. The integral of secant squared x will just give me tangent x, right? Likewise, when I take the derivative of secant, I get secant times tangent. So if I integrate secant x times tangent x, I'll just get secant x. Right? And same things for the cosecants and cotangents. Okay. All right. Here's something really, really important to note. In our earlier example, integration broke up over addition and subtraction, right? Constant multiples factor out. All of that's just fine, like differentiation. But we do not have product or quotient rules. Okay, let me give you an example. Suppose I want to integrate x to the 10th. I use my power rule. Add 1 to the power, divide by the new power. Done. Okay. Let's suppose I want to integrate the same function but written a different way. Suppose I want to write this as x to the 4th times x to the 6th. Okay. A very common mistake that I would see is, okay, integrate x to the 4th, right? Add 1 to the power, divide by the new power. Integrate x to the 6th, add 1 to the power, divide by the new power. Since they were connected by a times, I connect these with a times. And what do I get? X to the 5th times x to the 7th will give me an x to the 12th. And 5 times 7 is 35. So instead of an x to the 11th over 11, I get x to the 12th over 35. So doing the same problem two different ways gives me different answers. And that doesn't happen in math unless we made a mistake. And here we made a mistake, right? This is not, this doesn't work. We can't integrate a product, okay? Unless it's something clever like secant x times tangent x, right? That product I can integrate because I know something whose derivative is exactly that. But generally, we can't integrate a product. And that's not like a temporary problem. This is just a general difficulty with integration, right? If I think about the product rule for derivatives, right? If I take two multiplied functions, right, and differentiate them, I get f prime g plus f g prime. What that would mean is that going backwards, that means that the integral of f prime of x times g of x plus f of x times g prime of x dx would equal f of x times g of x. Okay, but like I would never recognize something like this. Would be really complicated. If I had functions in here, I wouldn't be able to pick out what the f and the g are that would make all of this work. Okay, so this doesn't really work well. So this is useless as an integration formula. Okay, so what I just want to emphasize is no product rules. Okay, you can't integrate a product. Okay, so let's look at an example. And of course, here's my first example, integrate a product, right? So you can't start by integrating because we don't have a product rule for integrals. So what we need to do is some algebra first to turn this into something that we can use our rules on. So what I'm going to do is I'm going to just distribute the x squared. So I have 5x squared minus 3x cubed. And now there's no more product. So now we can use our integration rules. So the 5 hangs out. I use the power rule on x squared. Okay. The negative 3 hangs out. I use the power rule on x cubed, and I get x to the 4th over 4. So we have 5/3 x cubed minus 3/4 x to the 4th plus c. And that's our integral. Okay. Similar story with this next one. I don't have a quotient rule for integrals, so I can't start by integrating. What I'm going to do is I'm going to rewrite this so that I don't have a quotient anymore. So I'm going to take x squared over x plus 4x to the 3rd power over x. Okay, and each one of these fractions I can simplify. X squared over x is just x. X to the 3rd over x is x to the negative 2/3. And now I can use my power rule. On x, I get x squared over 2, or I can write that as a half. When I integrate x to the 2/3, I add 1 to the power, so I'll get 1/3, and divide by that new power, divide by 1/3. Well, I don't like to divide by 1/3. I don't like to have layers of fractions. So when my power is a fraction, instead of dividing by it, I always just write multiply by its reciprocal. It's just a habit that I do to keep things from getting more complicated than they have to. Okay, so I have 1/2 x squared plus 12x to the 1/3 power plus c. Okay, for this next one, I have a product. I know I can't integrate it. Tangent x times cosine x is not the right one. I can't, that's not the derivative of something I know. Tangent x times secant x works, but not tangent x times cosine x. So I have to think about this one for a second and say, well, what can I do? And if I have a mix of trig functions and they feel like they're all over the place, or I just don't know what to do, one thing that I like as a strategy is to go back, bring everything back to sines and cosines. Okay, so if I rewrite tangent x as sine x over cosine x, cosine x is already a cosine x, then I can see, oh, here cosine x cancels. So now I'm just integrating sine x dx, and I can do that. Okay. Now I want to be careful. The answer is not cosine x plus c, because the derivative of cosine x is negative sine x. If I want to end up with a positive sine x, I have to start with a negative cosine x. So the double negatives cancel. Okay, let's look at a different type of problem. Initial value problems. All right, so if I write something like the integral of 2x dx equals x squared plus c, what I'm doing is I'm writing a family of functions whose derivative is 2x. So this is infinitely many functions. Sometimes I want to find a single function that solves a problem, right? So let's look at an example. Find a function whose derivative is f prime of x is 6x squared, but also that has the property that f of 0 equals 4. Okay, so there's going to be two parts to this. First of all, I need to find my function f. So what I'm going to do is I'm going to say, all right, find the integral of 6x squared dx, right? So that's going to be like my f of x, right? If I anti-differentiate f prime, I'll get f. Okay, so I use the power rule. So add 1 to the power, divide by the new power. So I get 2x cubed plus c. But then I also have this other property that f of 0 equals 4. Okay. So now I'm going to plug in f of 0 is 4. So f of 0 is 4, but when I put 0 into the function, I have 2 times 0 cubed plus c, and that's equal to 4. So c equals 4. So the function that I'm looking for is 2x cubed, but the c is 4, so plus 4. Okay. So just to give you a little bit of terminology here, this is called a general solution. Okay. This one down here is called a particular solution. Okay, and if I were to put some context on this, and remember that a lot of calculus, was largely done, right? All the basics were done, by Isaac Newton. And when people think of Newton, I don't think they typically think of him as a mathematician. You think of him as like the father of modern physics, right? So in a physics context, if I have like motion and my variable is time, then at time 0, that's at the start of whatever I'm modeling. That's why it's called initial value problem, because I'm looking at, okay, I'm told about something's derivative, right? If I think about motion, you can think of, all right, tell me the velocity, and then tell me where does it start initially, and I can give you a function for where that thing is at any time. Okay, so that's kind of like the outline of this. So what we're doing here with these initial value problems is sort of the basis for differential equations, where you have solving a problem that involves a function and its derivative. Okay, let's look at another example. Solve the initial value problem, so I know that the derivative of the function is 3x to the negative 2, and I know that the function, when I input 1, outputs 2. Okay, so one way to look at this is I'm going to take the integral of both sides. The integral of dy dx with respect to x is the integral of 3x to the negative 2 dx. And when I integrate dy dx, I just get my function y. The dx's cancel. I'm integrating 1 dy, and so I just get y. Okay, and for this function, I'm going to use the power rule. Add 1 to the power, divide by the new power. Okay, so I get negative 3 over x, right? So this is my function y. This is my general solution. So now I plug in to find the c and get a particular solution. So y of 1 equals 2. Right? So negative 3 over 1 plus c equals 2. So negative 3 plus c is 2. Add 3 to both sides, and I get c is 5. So y equals negative 3 over x plus 5. Okay, that's all there is to initial value problems. It's just kind of this extra step at the end where we solve for the plus c using some extra piece of information. And one of the things I want you to see with this example, even though we called it an initial value problem, we don't have to be, using like a time zero or anything like that. It doesn't have to be time anyway. It's just any other point on the graph. Okay, but historically, these were often like a starting value, right? When I'm setting up an experiment or something like that, I know where things start, and then I can model where it's going to end up at. All right. Any questions over this one?